Here is the Mendeleev's periodic table. Uh, as you can see, we have horizontal relations from beryllium. It starts from beryllium to magnesium. Still, there are similarities. Boron, aluminium. If you see the modern periodic table, they are in the same rows. And carbon, silicon, they are in the same family. But this time it is um, vertical arrangement, like uh, carbon 12 and carbon family. According to modern periodic table, carbon 12 and silicon are in the same family. uh, Nitrogen and phosphorus, according to modern periodic table, they are in the same group, to indicate they have similarity in property, chemical and physical. And oxygen and sulfur, they are also in the same family according to modern periodic table. So from this, what do we understand? Uh, Mendeleev tried to put elements according to their property. So fluorine, if you see halogens in modern periodic table, fluorine comes, chlorine, fluorine, chlorine, bromine, iodine, and the last one. Uh, so with this, they have got this in the same family, but still look in periodic table of Mendeleev's. Fluorine, chlorine, and bromine have got some similarity. But here is one odd behavior that we uh, uh, understand from this table. The first one is these are the empty spaces or question mark. This question marks, especially Mendeleev has left some elements whom he doesn't know, but he left a space by specifying the elements. So this is one of the extraordinary achievement of Mendeleev's, leaving a space for three elements. So Mendeleev left space in his periodic table for the elements yet to be discovered. So, as he said, later it was discovered later. Uh, so this. So he discovered later after his work, those three elements are discovered and exactly fit with his assumption. So these are gallium, germanium. The third element in the periodic table is and the other one is scandium. These are the three elements found. So he left three spaces for the elements yet to be discovered. So the three elements are here: gallium, germanium, and C. We will see, according in modern periodic table, how they are spaced or placed in the periodic table. So this is one of the achievements. And there is another shortcomings of Mendeleev. As you can see here, uh, he tried to arrange elements in increasing order of their atomic mass. If you see this element in the periodic table, tellurium is 128 and iodine is 127. So everything, the atomic mass was increasing in order. So if you can see 1994, everything is increasing. But there is an anomalous situation when you reach here 120 to 127. For arranging in this way, tellurium was in its exact place. But iodine, because of the order, there is a big. So here, according to him, in increasing order of atomic mass. So this is not increasing order. So now it decreased. So why this? Why this condition? This why this scenario or condition happen? Why this happen? The question. So it's maybe one of the reasons to shift from using atomic mass to arrange elements in a periodic table, not to use it. So the reason for this is what we call it isotope. Isotope. Some elements have heavy isotopes and with large abundance. So isotope, as a result, they have different masses. So, but if we arrange isotopes are atoms of the same element, isotope means atoms of the same element, having the same number of nuclear charge or number of proton, but different mass. So this difference in mass is caused by neutron. We will discuss it later anyway. Isotopes. That's why the disparity in mass changes. But we are going to fix this problem when we are going to use periodic table. So as we stated before, there are three components are missing. Three components of the modern periodic table are missing here. These are the noble gas. We don't have here noble gas. If you search here noble gas, we couldn't find noble gas. And another is the series. We call it the lanthanide series and actinide series. We cannot find here. So how these noble gases are introduced into the modern periodic table, we are going to see. So in Mendeleev's time, since noble gases are very inert or unreactive, he didn't notice their effect in his periodic table. So they are ignored because of their highly inert nature or complete unreactive nature of the group. So we are going to see after this lesson in the modern periodic table, we are going to go back to modern periodic table to see again the relationship. What is missing here? Look, we have here, and what we have seen as a limitation here. When it is completely changed using atomic number, we will see the difference.